All right, so let's break down the phenomena of what happens when we combine milk and acid together. What did we observe? Why does it matter? And how does it relate to cheese? To do this, let's observe really closely what was left in the filter and what went through it. Take a moment to closely observe the substances you see. So we see some sort of white substance that's gel-like in the filter and a clear-ish liquid that passed through the filter. From here, now let's go to predictions. What do you think these things might be? And even if you feel like you have no sense or no idea, you can try to think about maybe what we started with, what's in milk, and how that might relate to what's left in the filter and what went through. That white substance is casein proteins, and that clearish liquid is water and whey proteins. So you might be wondering what in the world those are. So let's actually go back and fully understand what milk is. And if we were to look and zoom into milk and look at the particles that make up milk, we'd see a variety of things. We'd see water. Actually, about 87% of milk is water. So we'd see a lot of water molecules. We'd see proteins. We'd see casein proteins and the whey proteins. We'd see sugar in the form of lactose. And we'd see fat particles, which are those big circles. We'd also see minerals like calcium, magnesium, so on and so forth. Now, specifically for this, we're going to focus in on the casein proteins. We saw the casein proteins separate out. What caused the casein proteins to separate out? Vinegar. But why? Well, to answer this, we're going to have to go even further back and understand casein proteins and how they exist in milk. In milk, we have thousands upon thousands of casein proteins, and they like to organize themselves into blobs called micelles. We're going to call them blobs from here on out just to keep things simple. But basically, this casein blob is thousands of casein proteins in this kind of coiled mess, all grouped together. I like to think of it like a bunch of wires or maybe a ball of yarn that's completely tangled up. Now, specifically, I want you to focus on the outside. And you can see here, what I'm doing with the wires is literally stripping off so it has an exposed end that is charged. And that's what we see with casein blobs in milk. Those exposed charged ends are on the outside. And originally, the casein proteins actually arranged themselves in a way that these charged exposed ends are on the outside. So the reason the negative charges on the casein proteins face out is because of another key component that makes up the majority of milk, water. Now, water molecules are made up of hydrogen and oxygen atoms, and the hydrogen atoms have a partial positive charge and the oxygen has a partial negative charge. And these charges are really important because those charges are going to influence what particles they're attracted to. So thinking about what a casein blob looks like with the negative charges on the outside and what water molecules look like with both positive and negative charges, how do you think the water molecules might interact with the casein blobs? The negative charges on the casein blobs will be attracted to the positive charges on the hydrogens of the water. And that's important because that attraction between the casein blobs and the water allows the casein blob to be soluble in water. When substances are soluble, they dissolve in the liquid that they're in, so in this case, water, and we cannot see the individual parts. So we can't see individual casein proteins in a commercial milk. The same concept applies to other substances like salt and sugar. Sugar and salt dissolve in water because they have negative and positive charges that are attracted to the charges in water. Okay, so let's get back to the casein blobs and how they interact with each other when in milk. The negative charges on the outside of the casein blob means that when one casein blob comes near another casein blob, they'll repel each other. That's because like charges repel or push away from each other, just like we would see with magnets. So we have these blobs of casein proteins that are repelling each other in milk. When we add an acid to the milk, these casein blobs change. When we add in vinegar or anything acidic, so that could also be something like lemon juice, we add protons or positive charges to the milk. So when we do that, where do you think the positive charges may go? What might they be attracted to? Well, it's just like magnets. Opposites attract. So those protons are going to be attracted to the outside of the casein blobs. When the positive and negative charges come together, they cancel out and they become neutral, so they're no longer charged. They have a neutral charge. And that is really important to thinking about how they may interact with each other. Now that they're neutral, what do you think will happen when one casein blob comes in contact with another? They won't repel each other, and instead they're going to come together, and that's what we see in those white solids. This neutralization also impacts how the casein blobs interact with water. Now that they're neutral, the casein blobs are no longer attracted to water molecules. It's as if we took an object that wasn't magnetic and put it up next to a magnet. There's no attraction or pull. Because of this, the casein blobs are no longer soluble in water. Instead, they're insoluble, and as a result, we see them essentially get pushed out of the water. They're more attracted to each other than the water molecules because they're neutral now. Sometimes this process is referred to as precipitation. All right, so just to recap, when casein blobs lose their negative charge, like when we add an acid, this results in two things. One, they can come together in a mass because they no longer repel each other. And two, they become insoluble in water, and so they get pushed out. Additionally, acids cause casein proteins to denature or unfold and lose some of their structure. Heat also causes proteins to denature, and it's often used in many cheese-making recipes along with acids. We often refer to this mass of casein blobs as curds in cheesemaking. Curds are the basis of all cheeses. Curds can look different depending on how they're formed and processed, like some can be cut or drained or pressed in different ways. You can also see in these other pictures, these are the mozzarella curds after they've been drained, and then we actually stretch and heat them, and that's what gives mozzarella its stretchy, shiny quality. It is important to note that not all cheeses are made with an acid like we use today. Some cheeses are, like ricotta, cottage cheese, and cream cheese. Others rely on microbes to produce those acids. So instead of directly adding an acid like lemon juice or vinegar, the bacteria that are naturally present in the milk produce this acid. Now, historically, this is how cheese was made and first discovered. Milk naturally had bacteria that produced that acid, which produced curds, which eventually produced cheese that we could eat, and that was easier to store as a nutritious source of food. Nowadays, most cheeses are not made this way because there can also be other bacteria that we don't want that may also grow and thrive in the milk. It's not very controlled. We really don't know exactly what we're going to get. So now many cheesemakers add specific bacteria and cultures that they know exactly what's in that culture, and it's much more controlled to do this job. Some examples of cheeses that are made with microbes or bacteria, specifically lactic acid bacteria, are feta, cheddar, and blue cheese. It's important to note that some of these cheeses also use other microbes, but that's not actually in the curd formation process. Other cheeses use an ingredient called rennet to form curds. Rennet can exist in the form of tablets or liquid. It can be made by animals, vegetables, or microbes. Rennet also neutralizes casein blobs, but in a different way. It actually contains enzymes that essentially cut off the negative charge on the outside of the casein blob like a pair of scissors. Cheeses made with rennet are mozzarella, provolone, parmesan, gruyere, Swiss cheese. There are so many that are made with rennet. So we've primarily focused on the science, but the history of cheese and why it was made in the first place is also really cool to think about. Cheese essentially solves a problem that milk spoils pretty quickly. Cheese, on the other hand, takes a lot longer to spoil. That's because it has less water and is more acidic, making it inhospitable for potential pathogens that might cause spoilage. So now that you have a basic understanding of how cheeses are made, what's your favorite cheese and how is it made? Take a moment to figure it out.